Hello, this video is intended to help review factoring binomials, the formulas that are involved in factoring binomials, and then applying these formulas to some trigonometric expressions. Let's first start with the rule for factoring the difference of two squares. So you'll note that you'll have the difference of two squares when you see two terms, and each of those two terms can be written as some value that's being raised to a power 2. So for example here I see 9x squared, which can be rewritten as 3x, that quantity being squared. Similarly 25y squared could be written as 5y to the second power. So when you have a perfect square value or quantity minus another perfect square value or quantity, that's when we know we have a difference of perfect squareds, and we can use that difference of two squares formula. Looking at the formula here, we can see it's a squared minus b squared. And how that factoring pattern works is you're going to have each of the values a and b, this time without any powers, written as factors. And one of the factors will be a plus, and one of the factors will be a minus in between those two terms. So for example, if I have x squared minus 9, this is the difference of two perfect square values. The first term is just x being squared. The second term is just 3 being squared. So in this instance, using my factoring pattern, I know my factors are going to involve x and 3. And the signs between those two terms will involve one being positive and one being negative. Now here it doesn't matter which one we assign the positive value and which one we give the negative value, because ultimately they're going to be multiplied together and yield the same result either way. So we know that we could choose either factor to be the plus or the minus. What matters is we're going to have one factor have the plus sign and one factor have the minus sign. Okay, let's try this a little bit more with some different looking examples. So the first example I see here, a, is 4x squared minus 1. My first thing to notice is that I have a binomial. There's only two terms, and I see a power 2. So when you have that occur, you have a two-termed binomial term that has a power 2. More than likely, we may have a difference of perfect squareds. So I'm going to use that same technique of writing this as two quantities being squared. So in this case, 4 is a perfect square number. It's 2 squared. Similarly, 1 squared is 1. So when I write it in that manner, it just becomes a lot easier for me to recognize those values, the a's and b's from our formula that we're going to use within our factoring pattern. So here, 2x and 1 are going to be the values that I use. One factor will get a plus sign, one factor will get a minus sign. So we can see on this example that once we identify what those values are prior to squaring, the factoring follows pretty easily. So looking at the next term, again I see a binomial and I see a power 2. So I'm going to try and rewrite this as the difference of those perfect square numbers. Y squared here is pretty easy. I know y, when multiplied by himself, will get me that y squared quantity. The 16 over 25 might trip us up though. So one key thing to know is that in fractions, you look at essentially each part, just the numerator, which is 16, and just the denominator to identify whether each of those would be perfect square numbers. So 16 is a perfect square. It's 4 times 4. Similarly, 25 is also a perfect square. He's 5 times 5. So 4/5, if it was multiplied by itself or squared, would yield that same 16 over 25. So using my factoring pattern, I know that I write down each of those values prior to squaring. And we're going to let one factor have a plus sign in between the two terms and one factor have a minus sign. Okay, looking at the next several, we should be able to figure these out. Again, I'm looking at a binomial with power 2's involved, so there's a good chance that we have that difference of perfect squares. So looking at the 36a squared, I know 36 comes from 6 squared, and 49b squared could be 7b, that quantity being squared. So again, I can see what those values are prior to being squared. I'm going to write those down, 6a and 7b, 6a, 7b. We're going to let one factor be a plus sign, one factor be a minus sign. And last but not least, I see a difference and I see two terms. I see a binomial, and I might automatically jump to this is a difference of perfect squares, but I'm going to get tripped up, and I'm going to get tripped up right here with the x cubed quantity. That's not a perfect square there. So I don't want to give up on this method just yet, because it could be that I do have a difference of perfect squares. There's just some other pieces that are preventing me from factoring it. So in this case, if I step back and I look at it as just a normal factoring problem, not necessarily looking at it as being a difference of perfect squares, I can notice that both of my terms have an x in common. So I can pull that x term out as a greatest common factor, leaving me with 4x squared for my first term and a negative 49 for my second term. And then anytime we factor, if you notice the instructions are to factor completely, that's because sometimes when we do one part of our factoring, it may reveal another factor that we can continue doing the factoring process on. And this is a good example of that. So I pulled out the greatest common factor of x, but then the 4x squared minus 49 can still be factored. Again, I'm looking at it as a perfect square and the difference of perfect squares specifically. So 4x squared could come from the quantity 2x being squared, and 49 can come from the quantity 7 being squared. So actually hiding in there was my difference of perfect squares. We just didn't see it because we had that extra greatest common factor of x that was being applied originally. So using the same factoring pattern, I know it's going to be 2x and 7, with one factor having a positive and one factor having a negative. So that would be our completely factored binomial. Let's look at a different type of factoring process for binomials, which is called the sum or difference of two cubes. So it's somewhat similar to what we saw for the difference of perfect squares. We're going to see some quantity being raised to a power. The difference here is that the power is going to be a 3. So say I have some quantity cubed added with some quantity cubed. The factoring pattern is you leave the first term without the cubes on them. So I'm still going to have a plus b, but this time with no cubes applying. And then we're going to have a trinomial as our other factor. So the first term of the trinomial is our first base, this a, raised to a power 2. The last term is our last term, b, being raised to power 2. And then the middle term are going to be our two bases, a and b multiplied. But we got to make sure whatever sign we have in our original statement, the sign for this middle term needs to be the opposite. So if you notice, this plus got changed into a minus right there. So using that same sort of process for the difference of two cubes, we can see the binomial term is the same basis and the same sign, a minus b, this time with no cubes on them. And then for the trinomial, it's the first term, or first base term a being squared. The last term is our last term b being squared. The middle term is each of them multiplied, but again, looking at the sign, it needs to be the opposite of what it was in the original. So originally it was a minus sign, now it needs to become a plus sign. So that's how I remember the pattern for this factoring method, is essentially what I described here with keeping the bases the same or squaring them or negating the sign. So let's look at our binomials. So again, I see a binomial and I see a power 3. That's a good indicator that we're going to have this sum or difference of our perfect cubes. To make it easier, we, similarly like we did for the difference of perfect squares, want to write what the bases are prior to this power 3 or cube occurring. So for x cubed, my base needed to be an x raised to the third power. For 1 times 1 times 1, or 1 cubed, yields me that 1. So I'm essentially identifying the a and the b here from our factoring pattern. So using this, I know that my first binomial term is going to be just x plus 1. The trinomial term is going to be the first term x being squared, the last term 1 being squared. In the middle, I'm going to multiply them. And I want to make sure that middle term is the opposite of what it was to begin with. So originally I had plus, that means I need a minus. So I'm just going to simplify this a little bit for the trinomial part, squaring items and then just simplifying the multiplication. So x squared, the middle term is going to become negative 1x, or just negative x. We don't necessarily have to write the 1 there. And then plus 1 squared, which is 1. So that's our factoring pattern for a. Now for b, Again, I am seeing a binomial and I'm noticing a power 3, so that's a good hint that we're going to have the sum or difference of cubes again. And so we want to take that same technique of writing what the bases are. So y cubed gets me my first term, and then 64 I might get a little stumped on. If you don't know your perfect cubes all that well, which isn't uncommon, we usually know our perfect squareds, but maybe not the perfect cubes. You can go through each of the prime numbers and try cubing them. So 2 cubed is 8, 3 cubed is 3 times 3, which is 9, times another 3 is 27. 4 cubed is going to get me 16 times 4, which is our 64 there. So that's one technique. If you don't know your perfect cubes, just go through that list until either you've gotten the number that you think is a cube, or you've realized that it actually isn't a cube. So for instance, if this was 62 and I went from 27 to 64, I know that this isn't a perfect cube, and so it doesn't fit our factoring pattern. In this case it works. So 4 cubed, I'm going to use that same pattern. I'm going to write each of the values without the power 3 for the binomial term. I'm going to take the first term and square it for the first term of the trinomial, the last term and square it for the last term, and then we're going to multiply 4 and y, and then I have to negate the sign. So I originally had a minus. That means that my value needs to be a plus there. And we can simplify this a little bit. For the trinomial, I can go ahead and simplify the 4 squared to be a 16. Alright, so now that we know each of these perfect square factoring methods and the difference and sum of cubes squared methods, let's go ahead and apply these same ideas that we saw from algebra to now trigonometry. So now we have some trigonometric expressions that we also want to factor in a similar manner. So here I can see again I have a binomial and I see power 2. So similar to what we did for difference of perfect squareds, we want to write what those might be prior to being squared. So tangent squared came from taking the tangent of our angle theta and squaring him. Similarly for cotangent squared, that's our cotangent being squared. So this is that same a and b that we saw from our difference of perfect squareds factoring pattern. So we can use that factoring pattern in the same way. So I can write down those two values, the two bases, and one of my factors is going to have a plus sign in between those two values, and one is going to have a minus sign. Now here we want to be very careful because it says factor completely. So I don't have any other powers occurring here. Everything is linear or raised to the power 1. If I saw some power 2 values, which sometimes that may happen, that means I'm not done in my factoring process. But if everything looks linear and you don't see any common factors that you can factor out, that's a good indicator that you are in fact done and you factored everything completely. Now B actually isn't a binomial, he's a trinomial, but we can again take this idea of I'm using algebra and our factoring rules from algebra to help us solve these trigonometric expressions. So this to me looks kind of similar to 4x squared plus 8x plus 4. Essentially what I did is I replaced the sign y statement with x. So I know how to factor this guy. I would use 2 binomials to factor him. It's going to be the same thing for our sign statement. We're going to break this down as 2 binomials. So the first thing that I want to look at is the 4 sine y. So 4, I know I can break down as 2 times 2. And the sine y to the second power can come from multiplying sine y by himself. So I'm just factoring the first term in our trinomial to create the first of each of my terms in the binomials. Then for 4, I know 4 can be factored into 2 plus 2. I want the result when I multiply to be positive, and when we add our terms to create the middle term to be positive. So I know that each of these is positive. And then to check that I've done my factoring correctly, we're going to multiply the outer set of terms and the inner set of terms and see if we get that 8 sine y when we're done. So 2 times 2 gets me 4 sine y for the outer set of numbers. For the inner set, 2 times 2 also gets me 4 sine y. And when we combine those, we do in fact get the 8 sine y. So I know for sure that I factored my expression